What if I told you that this pure gold, one of the densest materials on Earth, is almost completely empty space? I'll prove it by creating one of the most iconic experiments in history, the Rutherford gold foil experiment. In this demonstration, I'll show you that the atoms making up gold, rocks, and even you are almost completely empty, except for a tiny nucleus that takes up only about a trillionth of the atom's volume. At the turn of the 20th century, the true nature of the atom was still a mystery. In 1897, J.J. Thomson discovered the electron and proposed what became known as the plum pudding model of the atom. This model suggested that atoms were blobs of positive charge with tiny negative electrons embedded inside, like raisins in a pudding. But in 1909, Ernest Rutherford, working with alpha radiation, set out to test this idea. Alpha radiation is a stream of fast-moving positively charged particles, each consisting of 2 protons and 2 neutrons, essentially the nucleus of a helium atom. Since these particles were massive and positively charged, Rutherford wanted to see how they interacted with a positive charge in the atom. So he decided to fire alpha particles at thin sheets of different materials. What he found completely changed our understanding of the atom. To recreate this experiment, I'll be using a small button of americium-241, which spontaneously decays into neptunium-237, releasing an alpha particle. I'll also use a Geiger counter that can detect alpha particles, and then a thin sheet of gold to see what happens when alpha particles pass through it. Now, alpha decay is rare. Every minute, an americium-241 atom has about a 1 in 330 million chance of decaying. But with 10 to the 26 atoms in this bead, decay is constant, and we can hear every time an atom emits an alpha particle. You can see with my Geiger counter here, I have it set to alpha. Watch what happens when I stick it over the source. Every click represents an alpha particle hitting the detector. Also, notice that the particles only come from the front in a concentrated cone. That's because heavy metal shielding on the back blocks the other directions, meaning all escaping alpha particles are directed straight ahead. You can see from the side, I can't measure any alpha particles. But as soon as I move it in front of it, it goes crazy. Over here, behind it, I don't measure any increase. Now let's set up the experiment. I'm placing the gold foil in a vacuum chamber so we can measure only the interaction between the gold and alpha particles without air interfering. Also, this setup allows me to move the detector to different angles and measure what happens. So let's vacuum out the air and take our first reading. So first let's measure it without the gold in place. Okay, now without the gold, with the source just directly behind the Geiger counter, let's measure how high we're getting. We're at 3,900. We get about 4,000 clicks per minute. Now let's do the same thing, but we're gonna place our gold in between the detector and the source. Now move it directly in front of the source. Take our measurement. Okay, we got 3,800. You can see that the click rate is almost unchanged, still about 4,000 clicks per minute. That means almost all the alpha particles are passing right through solid gold. This is crazy. They're just shooting right through it. Now let's pause for a second and absorb what's happening here. This is incredible. I'm not shooting X-rays or light waves that we already know can pass through materials. I'm firing real massive particles, the nuclei of helium atoms. They have mass and volume, yet they're flying straight through solid gold. But why? It's because while gold feels solid, its atoms are mostly empty space. The atomic orbitals of gold are about 0.288 nanometers in diameter. But the nucleus is just 8.5 femtometers, meaning gold atoms are 34,000 times larger than their own nucleus. If the nucleus were the size of a marble, the rest of the atom would be as large as a football stadium, and nearly all of that space is empty. Electrons in these orbitals don't stop the alpha particles either. They're too small and too light, The alpha particles like a bowling ball smashing through ping pong balls. The alpha particles just keep going. At this point, scientists in 1909 wouldn't have been too surprised by what's happening here. Even in the plum pudding model, alpha particles were expected to pass through the atom, maybe slowing down slightly or being slightly deflected. But here's what no one expected, what destroyed the plum pudding model forever. Rutherford moved the detector to the side and behind the gold, places where if the plum pudding model were correct, no alpha particles should ever reach. So let's try it and see what happens. Before we continue, for this experiment, we know how important good suction is. Not just in a vacuum chamber, but in a vacuum cleaner. That's why I want to tell you about the MOVA P50 Pro Ultra. With an industry-leading 19,000 Pascal suction power, it effortlessly removes dust, hair, and debris from any surface in just one pass, even on carpets. Watch as it tackles this mess with ease on my carpet here. One of the coolest things about this MOVA vacuum is how it keeps your carpets from getting dirty water on them. For carpets with long fibers, you can manually select the mop removal feature in the MOVA Home app.
Mop pads removed.
And the vacuum literally detaches the mop pads before going to your carpet. If you don't have that selected, then it'll automatically lift the side brush to 10 millimeters high and the mop pads to 10.5 millimeters above the carpet. It automatically empties its dustbin for up to 75 days and cleans its mop pads with 75 degrees Celsius hot water, drying them with 45 degrees Celsius air, all from the base station. Another really cool feature is that the mop and the side brush extend out the side to get the hard-to-reach corners. Equipped with advanced sensors, the P50 Pro Ultra intelligently detects and avoids obstacles, ensuring seamless navigation throughout the home. The P50 Pro Ultra is now available for pre-sale. Secure your spot now using the links in the description and lock in the early bird price for when it becomes available. Now let's get back to our experiment. Now for this setup, I have something a little different. So I've got my source right there and it's aiming this way. And then I have my detector behind it. So the only way those alpha particles could hit the detector is I can move my gold now in front of the source so that they could bounce off the gold and hit the detector. So when I've moved it out of the way, there's no gold that could get hit by the alpha particles. Then I get a background radiation of 18.9 counts per minute. So in 1 minute, 18.9 alpha particles hit the detector. So that's just what we expect from the background. Now let's move this in front of it. Now the alpha particles can hit the gold and bounce back. Start measuring. Now at the end of the measurement, on this minute, we have 23.6 particles that hit it. So we got 4 more particles per minute hitting the detector. Now that doesn't seem like a lot, but that's because, as we learned before, the gold is mostly empty space. So most of the alpha particles just fly right through, but about 1 in 10,000 bounce back off the nucleus of the gold atoms. Rutherford realized that the only way alpha particles, so heavy and fast, could bounce back like this was if they hit something far more massive than themselves. By calculating the probability of alpha particles scattering, Rutherford concluded that almost all of an atom's mass must be concentrated in a tiny central point. He called this the nucleus, a small, positively charged, highly dense center of the atom. I can change the angle of the detector and see that right behind the gold, most of the alpha particles are going straight through. But if I move it a little to the side, the detector still picks up radiation above background levels, even at extreme angles and even behind it. The only way to explain this is with this new type of model that Rutherford explained. This model laid the foundation for modern atomic physics, eventually leading to Bohr's refinement, which introduced electron energy levels. It's so incredible that one of the most important experiments in physics can be recreated with a relatively simple setup like this. Also, as we discovered in this video, alpha particles pass through atoms unless they hit a nucleus, which is rare. But remember, materials contain an enormous number of atoms. This means that even something as thin as a piece of paper has enough nuclei that eventually all the alpha particles will collide with one and be stopped. You can see how all the radiation basically stops if I just slide a piece of paper in between the detector and the source. In fact, even a few centimeters of air contain enough atoms to stop the alpha particles completely. If I move my detector far enough from the source, you can only hear background radiation. But once I bring it closer, the alpha particles can reach the detector because there isn't enough air in between. Now you can see why the gold foil had to be so thin in this experiment, and why we needed to conduct the experiment inside the vacuum chamber. This also explains why alpha radiation isn't dangerous in this setting, because my skin blocks it completely. However, it can be extremely dangerous if inhaled or ingested. If you were to breathe in americium particles or ingest them, the thin tissues inside your body would be constantly bombarded by high-energy alpha particles, which would be very damaging. And thanks for watching another episode of the Action Lab. I hope you enjoyed it and learned something. If you did, don't forget to subscribe to my channel if you haven't yet, and we'll see you next time.